We're going to look at another way to use a chi-squared table, and that's or a chi-squared test, excuse me, and that's to use a two-way table test. A lot of these we've seen these already, where you have different classifications. For example, on the last test, when we had the Titanic problem, where you had if it was a man, a woman, or a child, and whether they survived, they died, right? A lot of that stuff with the probability, these were two-way tables because they were comparing a lot of different things at once. Chi-squared can be a really good distribution for this, and one of the ways we can do it is what's called a chi-squared test for homogeneity. In other words, the word homogeneity, are things the same? Are things equally distributed among the groups, right? So a chi-squared test for homogeneity is used to determine if choices are the same among different groups. In other words, are things kind of equally distributed among the different groups? Our hypotheses here. So the null will be the distributions are the same for each group. And the alternative, the distributions are not the same. Here we go again, where we have opposites in our null and our alternative hypothesis. The conditions for this test, same as before, random and big enough. Again, just like we saw in the chi-square goodness of fit test, if all the expected are greater than 5, you can put that. And really all we're doing again is data from a random sample here, and is data from a replicated sample, or have they done it a lot? So we got randomness and replication. Here it is again. Here, degrees of freedom is going to be slightly different because we have a two-way table. You can take the number of rows, subtract 1, and multiply that times the number of columns minus 1. So here's an example that we have. So reports on 4 colleges on the postgraduate activities for their 2006 graduating class. Are the students' choices the same across all colleges? So in other words, one way to think about this, there's obviously, a bigger number if we fill in the totals, right? So we have 1,052 that went and got jobs, versus 722 that went back to school, right? But really, what we're looking for are the students' choices the same across all colleges? Well, there's a fewest number of social sciences, and these two are about the same in agriculture and art science, right? So when it's saying, is it the same? Are we seeing about the same number of ag students and arts and science students going to get a job right out of school? Are we seeing about the same number going to grad school? Now, obviously, this 125 over here is smaller, but in terms of a percentage, you could think about it this way. Are the percentage of students from each school going and getting a job? Are this about the same percentage of each one of these 4 schools? So do we have about the same percentage of engineers doing something else as those that are in the social sciences doing something else? Obviously, the numbers might be the same, but are the percentages the same, right? That's kind of what we're looking for. So that being said, to find the expected counts, what we're going to have to do is row total times column total. Oh, I don't know why that turned into tall, but column total over n. So for employed, you take the row total, so just so you can see it, that's 1,052 times the column total, 669, over the overall total, 2,096, right? To get the grad school agriculture, so you go to the row total 722, column total 669, over 2,096. Now you'd end up with these numbers. Now I'm going to show you in just a minute a quicker way to get that. But that's where all these numbers are coming from. There's still a formula that you're going to follow to get those. Remember, expected counts can have decimals. Not a big deal. So we're going to run a chi-squared test for homogeneity. In other words, real quickly, the conditions, the data is, we didn't say it was random, so we're going to assume. And here, all of our expected values are bigger than 5. Right? Go back and look. Right? 335, 334. In fact, here's the smallest expected value at 42.86. So our conditions are met. Degrees of freedom, 2 times 3. So again, number of rows, right? So we have, this is a 3 by 4 matrix. So we do rows minus 1 times columns minus 1, 3 times 2 equals 6, right? So there's your degrees of freedom. And then, so what we would expect if the activity is distributed equally among each college, again, not necessarily by total counts, but by percentages. And then the alternative, the activities are not distributed the same for each college. Um, kind of like we did before, I'd like to see you write out a few of these. I'll show you how to get that chi-squared value in just a minute. That's a pretty big chi-squared value. And if we were to see that shaded on the calculator, it's way out at the end. So our chi-squared, the probability that we're there, again, if we did it in the calculator, it would be the chi-squared CDF. Oops, I put parentheses in the wrong place. From 54.51 to infinity. And this time we had 6 degrees of freedom. It's essentially 0, right? This is a really, really big chi-squared value. So it looks like, and if you think about it, probably depending upon what your degree was in college, that might kind of dictate whether or not you move on to the next level of schooling or if you just go get a job right away. Remember that the most commonly used cutoff value is 0.05, so we're definitely going to reject the null here. And so it appears the proportions are not all equal. The activities are not the same for each college. Let me show you how this could play out in the calculator. I'll show you where these numbers are coming from. Again, an in-between step here, which would be really nice to see, would be to write a few of these values in. 379 minus 335. Right, to do the 379 minus 335 point whatever squared over the 335 point, and then plus, and then maybe do the one at the end. Be good to see that, so we're showing that we know what to do. But let me take a moment. I'll show you how you can come up with this stuff in the calculator. Again, we want name of the test. There's our hypotheses. We check the conditions. Right? Jotted down our degrees of freedom. We're showing we know how to use the formula. Here's the actual chi-squared value, right? They kind of wrote their probability statement a little bit differently. We would have just written p-value is essentially 0 right here. We got the inequality. We've got our decision to reject, and then we write our answer back in context. The same kind of process as yesterday. Here's how it works in the calculator. What you're going to do is actually put your two-way table into a matrix. So I went ahead and did that on the front side. You can see here that I put it into matrix A. All right, so if you want to remember how to get here, I can kind of show you again. So if you hit second matrix, and then you want to go over and edit matrix A, and then you just type your data in. No row totals, no column totals. Don't put the totals in there, just the actual table itself. Now from here, every calculator has access to this. Go back into stat and go to your tests. If you scroll down, there's just a chi-squared test. We can get to it. A chi-squared test. And this one's asking you observed, expected. Now, the nice thing about this, we've got our observed data in A. You actually don't have to put the expected value into B because the calculator will do it for you. What you're essentially telling your calculator here is, this is where I put my original data in A. I would like you, Mr. Calculator Man, to figure out the expected values and put them into B. So here, just going to hit calculate. So there's that chi-squared, 54.51. And this is 5.819. Make sure you go all the way to the end. Notice that's e to the negative 10th. So that's 0.000000006. That's essentially 0. Here again, it tells you your degrees of freedom at 6. And then what I would want you to now do is go back into matrix and look at that. They have done something to B. And if you go over, you can see what B looks like. I usually just go to the edit. And then there are the expected values, right? 335.78, 334.27, right? If I go back in here, 335.78, 334.27. So that's the really nice thing about the calculator is actually we're going to run the test, and then we can go back in and fill the expected values in after we finish.